Have you ever stopped and looked at the power brick for your phone or your laptop and thought, wait a minute, didn't this thing used to be way bigger? Well, you're not wrong, and it's not magic. What you're seeing is a massive revolution in material science, and it's happening inside one of the most boring but most important pieces of tech we all own. So what is the secret behind this incredible shrinking act? Let's dive in.
So, yeah, why did it shrink? I mean, you're getting the same amount of power, sometimes even more with all this fast charging stuff, but the adapter itself is just a fraction of the size it used to be. The answer to that question comes down to three letters: GaN, gallium nitride.
And this just lays it out perfectly, doesn't it? I mean, look at that. On the left, you've got your classic, chunky, silicone-based power supply. And on the right, its modern equivalent, using gallium nitride, or GaN. It's about a third of the volume, but it's putting out the exact same 50 watts of power. So how on earth is that possible?
All right, to really get what's going on here, we first need to pull back the curtain and understand the invisible engine that makes our entire modern world work. We're talking about power electronics. So what is power electronics? You can think of it as the ultimate traffic cop for electricity. It takes the wild, raw power coming out of your wall outlet and skillfully tames it, converting it into the exact, precise, stable voltage that all of your sensitive devices need to survive. It's the unsung hero working in the background of pretty much everything you own. So how does this brain actually work? Well, at its heart, it's basically a tiny, ridiculously fast switch. And when I say fast, I mean it's flipping on and off millions, sometimes billions of times per second. This rapid-fire action chops up the electricity into these little pulses, which are then smoothed out to create that perfect, clean stream of power your phone needs. And the speed of that switch? Well, that turns out to be everything.
And that little detail, the speed, brings us right to the heart of our story. This isn't just about a new material. Honestly, it's a real David versus Goliath showdown. You've got the long-reigning champion, silicon, being challenged by this scrappy newcomer, gallium nitride. So let's put them head to head. For decades, right, silicon has been the undisputed king. It's reliable, it's cheap, it gets the job done. But for this specific job, GaN is just better. It can switch on and off way, way faster. And because it's faster, it's more efficient, which means it wastes a lot less energy as heat. And less heat is the magic key that lets you make everything smaller and lighter.
You know, the folks over at the YouTube channel Electra Arc 240 put it perfectly in one of their teardowns. They said a jump in efficiency from 85% to 92%, it might not sound like a big deal, but think about what that means. You've just cut the amount of energy being wasted as heat by almost half. That is a massive, massive deal.
And here's the proof, right here in the numbers. When you're pushing a full 50 watts, that old silicone brick is just bleeding out about 8.8 watts as pure, useless heat. The GaN charger? Just 4.4 watts. That's a huge improvement, and it's the entire reason GaN chargers can be so tiny. They just don't need all that extra bulk and metal to get rid of waste heat. So what's the secret sauce here? It all comes back to that one thing: switching frequency. The fact that GaN transistors can flip on and off so much faster than silicon ones creates this incredible domino effect that changes the design of the entire power supply. And this is where it gets really cool. Just look at how that domino effect plays out. A faster switch means you can use a much smaller transformer. In the GaN supply, it's so small it's literally printed right onto the circuit board. Those big, bulky capacitors that smooth out the power? More than 10 times smaller. A faster switch literally makes everything else on the board shrink right along with it. Okay, but you knew there had to be a catch, right? When you pack more power and more speed into a tinier space, you create a new problem: heat. And that brings us to the next big challenge. How do you manage all that thermal energy? Sure, your tiny little phone charger might be fine just sitting there, but what happens when you scale this tech up? Think about data centers, electric vehicles, massive solar farms. The question becomes absolutely critical. How do you stop these tiny, powerful engines from melting down? Right, so for these high-power systems, just blowing a fan on it isn't going to cut it. Engineers are getting really clever. They're using direct liquid cooling, basically pumping a coolant right over the hottest parts of the circuit. And for the most extreme cases, they're using something called immersion cooling, where they literally dunk the entire electronic system into a special non-conductive liquid just to pull all that heat away. But here's an important point. GaN isn't the only tool in the toolbox.
As amazing as it is, a good engineer knows you have to pick the right component for the right job, and there are other options out there. For example, for a lot of smaller, high-frequency stuff, engineers might still use a classic silicon switch called a MOSFET. It works great, but for the really heavy-duty jobs, like powering the motor in an EV, they'll reach for a different beast altogether, an IGBT, which is designed to handle enormous amounts of voltage and current. It's all about picking the right tool. So this revolution in materials is amazing, but it's really just the beginning. The next giant leap forward is what happens when you take all this incredible new hardware and you give it a brain. We're entering the era of smart power. Yeah, we're shifting from an age of just having better, faster components to an era where the power systems themselves are becoming intelligent. They're starting to think. And that, right there, is where things get really, really interesting. And when you look at the big trends, you can see how it's all connected. GaN and other new materials are becoming the new standard, the foundation. But on top of that, we're layering AI for real-time control, IoT so these things can talk to each other, and a huge focus on sustainability. It's a whole new ecosystem. And hey, don't just take my word for it. The academics are all over this. This review basically says that machine learning is becoming essential. It's the key that lets these power systems adapt to change on the fly and squeeze every single last drop of efficiency out of the system. So what does that actually look like? Well, imagine a power system that is constantly learning, watching its own performance data. Then it starts to predict the future, seeing when a component might fail before it even happens. And finally, it optimizes itself, constantly fine-tuning its own settings in real time to be as efficient and reliable as possible. It's a system that's always improving. And this all brings us to one last, really big question. We started this whole journey with a tiny little power brick that got smaller thanks to a new material. But this same combination of advanced materials and artificial intelligence is now scaling up big time. So what happens when our entire power grid, the single largest machine on Earth, starts to think for itself? The future of power isn't just about smaller chargers. It's about a smarter, faster, and way more efficient world for every single one of us.